So second problem that I'm going to talk about is very controversial. And I can tell you that I am definitely the minority in this community about this problem. And this is the many model problem resulting from parameter uncertainty. And by now, I hope you all agree that this is a problem when you model certain chemistry problem in combustion. You have to worry about parameter uncertainty. I showed you the good, the bad, the ugly case in terms of uncertainty. Now, because of this uncertainty for this rate constant, I can choose, let's choose the ugly case. Start from there. That case. Nobody will tell you when you publish reaction mechanism, if you put a rate constant, this is your choice. No reviewers will tell you it's a wrong choice. And if you choose something like that, nobody will tell you it's a wrong choice. This is just the information we have. You can justify every possible way within this order of magnitude about the value of the rate constant. So each and every research group has our pet rate parameter. This is what we like. You ask us, why do I like that? I may be able to spend half day to tell you why I like this rate constant in this way. But each of us have different flavors, different objectives, and so on. That leads to this problem. All right. The net impact on things I see. I was flipping this too fast and now it's frozen. Come on, don't do this to me. All right, I have to restart it. My apologies. And if I can restart it. While my computing is rebooting, I want to tell you one thing I always tell my students when I teach thermodynamics. Okay? I would show them a picture of the Boeing 87, the GE engine. And I invite them to take a look at this monster. And I told them that how many of you had your cell phone crashed yesterday? 10% of people will just raise their hand. I said, what if I design an engine with 10% of the time it will crash? I said, oh no. So I said, then let's put things in perspective. Between what we call today propulsion, no longer considered to be high tech, versus cell phones. Which one do you think actually is the high tech? The answer is obvious. Is this the right lecture? No, yeah. My apologies for the technical difficulty. All right. So this situation has led to, if we were to adopt a linear process, what I call two-model development, you would start from a critical review of literature kinetic data. Sometimes this is done for you already by various people. You compile a model, and you do some tuning. Through sensitivity analysis, you will do some validation against a certain set of experimental data. You're done. You publish your model. And as a student, you graduate. thesis is done. The next student will come, will do exactly the same thing. And you end up with many models. Okay? And that situation has caused this problem, what I call proliferation of models. When you have too many models, they're not intercompared. We actually don't learn much. After all, if you have thousands of parameters, you only have something like a tens of couple dozens of observations. It's an EO-defined mathematical problem. You have more unknowns than the number of equations you have. Therefore, it's inevitable that you're going to see this situation. The question is, what do you do about it? And if you look at the combustion of flame today, about half of the paper published is about reaction mechanisms, about reaction models. And when you see a line going through experimental data, because it's EO-defined mathematical problem, you could have found many different combinations of a parameter all reproduce the same set of experiments. So therefore, you actually do not know how good your model is. So this is the type of business that running come to today. When I review a paper, when I see model prediction going through the data, I do not know if the model is good. If the model does not go through the data, I sometimes get excited. Maybe I'll learn something. Okay. The publication business and getting your thesis and so on, because you always have to worry about cheap shots. Cheap shots by somebody sitting in the audience. You say, hey, you're way off. You're off by a factor of 2. Something must be wrong with your model. The implication is, A, your paper has problems and it should not be published, or your thesis work has problems. And you never want that. You always like to see agreement. But keep in mind, agreements don't necessarily mean a model is good. Number one. Number two, this linear process is going nowhere for us. That's my own opinion. And it will allow your generation to really solve this problem. Harder problem, cause a problem you know, and you know very well. Okay? All right. Underlying problem has to do with uncertainty. Okay? If you take the H plus O2 reaction, now this is data a little old. I did not add the new data published by Professor Ron Hansen. So let's assume I have 50% uncertainty up and down, so the uncertainty factor is about a 1.25. Okay. If you look at the logarithmic sensitivity coefficient, that's the derivative of natural log of flame speed with respect to natural log of rate constant. I find this value typically is around 0.2, 0.3. In this case, for an ethylene air mixture at a stoichiometric condition. You take the 50% uncertainty, translate into how much uncertainty in prediction. That's plus minus 4 centimeters per second. But that is just one parameter. You have many more. It's cumulative. Okay? And that's what's responsible for rate constant uncertainty. In a way, how you look at the predictions. And this is a classical chart now done by Professor Michael Burke at Columbia, and then a student here at Princeton working with Yu Guangqu and Fred Dreyer. These are the many models published within the last 10 years or so on hydrogen oxidation. Remember, hydrogen oxidation is the very foundation of this whole thing. And prior to this set of data were measured, we have some data mostly at ambient pressure. When you get to higher pressures, none of the models have been tested under this condition. So I'm sorry that I have to do this again. So when you get a model, you compare to the data, you say, oh, this is very bad. This is bad, this is bad, this is bad. Uh-oh. And they're lucky. They're lucky. Because without this experimental guidance, when you hit the data, you actually don't know why you hit the data. Okay? So the point is, when you see a disagreement, this does not mean the model is bad. It's just because the rate parameter has its uncertainties. And in this case, you happen to hit it, the experiment. And if you move to some other conditions, this model actually doesn't predict the data very well. We develop a model as far as application is concerned, is for us to use the model to extrapolate. already. And if you were to interpolate, you already have the experiment, so why do you even bother with the model? From application standpoint. Fundamentally, of course, you still can learn something about what's going on. So this has been the problem. So how do you solve? The root of the problem, of course, I will explain this again. Rate parameter uncertainty, let's suppose this region represents some kind of a high dimensional rate constant uncertainty. Okay, there are many of them. And this is some fundamental combustion data, let's say the laminar flame speed. The experiment data, of course, has some uncertainty. Look at the error bar here. There's some error bar here. So this is not a point. This is some kind of region. You take the physical problem. Let's say in that case, a set of governing equations governing the laminar flame speed. And this uncertainty, of course, expands as you go through the physical problem into this large space. All right? Any model is a single point in this parameter space. It's just a one unique set of rate parameter. And each point runs through the physical problem is going to give you another point in prediction. For example, a laminar flame speed value. Obviously, I can populate infinite number of points to generate an infinite number of points in my flame speed. Now, once I recognized this problem back in about 2004, a little more than 10 years ago, I stopped the publishing reaction mechanism. I completely stopped. And I do have model published on the web. It's just because I could not justify to myself what I contribute scientifically by formalizing my reaction model into a paper. For that particular model, it's just a random point. And therefore, if you push me a little more, I would say it's a random model with some physics in it. All right. So how do we move forward? If you agree with my assessment, then this is a problem we have to address. Okay. So last few years, we put a bit of a time, along with then my student, David Xing, on this problem, and asking the question, can you systematically propagate that parameter uncertainty straight into simulation? In other words, when we make a prediction about the flame speed, can you also predict the error bar? Okay? And if you have this computed error bar, by comparing to the experimental error bar, can you propagate this information back? In doing so, reduce the uncertainty of the rate parameter. In other words, shrink the space. Alrighty? And in a way, we are modeling after meteorology people. In meteorology community, making a prediction for the weather matters. Okay? And it's important. And it saves lives. Therefore, quality of prediction matters. In meteorology, you never say tomorrow is going to rain. We talk about, oh, it's going to rain tomorrow. Guess what? That statement is a prediction. More importantly, as a matter of fact, that statement is an opinion. A prediction must include a statement about how good that prediction is. So you always hear with a 50% chance tomorrow is going to rain. What does that mean? You have quantified the accuracy of your prediction. With that knowledge, now you can make a decision. What do you do with it, this information? Again, 50%. If it's me, I won't bring an umbrella. I bet on that 50% chance it's not going to rain. My grandma, when he was still alive, would definitely bring an umbrella. Even 10% chance of rain, she would bring an umbrella. It's how we make our personal choices. But that 50%, 10% matters. Would you agree? Okay. You say it's going to rain tomorrow, doesn't mean that much. If you say it's going to rain 100%, but these two statements are not equal. You say with 100% probability tomorrow is going to rain versus tomorrow it's going to rain. These two conclusions are entirely different, as a matter of fact, as far as how you use this conclusion. So this is exactly what we want to do. We're going to quantify how good my prediction is. And from there, you ask the question, what I can do to make the prediction better. So the way how this works, this is one of the many methods. And I'll just tell you our methods, and don't get locked onto this whole thing. There are many even more efficient methods, perhaps. But it illustrates something that's actually very simple. Suppose you have some parameter. Let's say this is the rate parameter. I don't use K, I use X, because X can be anything. Can be rate parameter, can be enthalpy of formation, can be transport properties. Okay? And this is our monominal value. So let's suppose you evaluate a rate parameter. This is the value you get. Okay? That's those lines in the middle. Then you have uncertainties. The uncertainties is represented by those terms. First order, higher order terms. And those are random basis functions to account for the distribution of the uncertainty. Then this rate parameter from a single value is expanded into a nominal value plus its distribution. All right. Then you look at some combustion response. Let's say I have a laminar flame speed. The laminar flame speed, in fact, is dependent on the parameter for the prediction you make, is about the parameter you choose. You again expand the prediction with respect to the parameter. And in this case, a second-order polynomial. That's just for numerical convenience. You can choose any function to represent that. All right. And you can get this type of equation by pre-running many combustion flame simulations and do a regression. Do a regression to get this equation. Does that make sense? Okay. And then when you combine this thing together, your final prediction is made of the impact of variation of the rate parameter plus their uncertainty all built into this prediction itself. So this is called essentially from deterministic prediction to some type of fuzzy prediction. Once you do that, then this picture I showed you earlier now suddenly all makes sense. If we take all the parameter uncertainty into a model, asking what's the standard deviation of the hydrogen model, then this is represented by this dashed line. 2 sigma up, 2 sigma down, the S should be sigma. And then all the models that are shown here are bracketed by this uncertainty band. That is, in fact, the fuzziness of, reflected the fuzziness of our knowledge. Okay? Now, then you notice that experimentally the uncertainty is far smaller than the computed uncertainty. So the experiment must embed some useful information that you can utilize. You can project this part of knowledge back to the model to constrain the parameter uncertainties. And this is the method that involves, let's suppose this is your experimental uncertainty, this is initial model uncertainty, then this is all about you project this space back here, leading to a narrowed parameter space. Okay? The goal in defining new experiment over here is about intersecting those spaces. Those are all high dimensional. If you have 20 rate parameters that are uncertain, then you have 20 dimensions. But if you intersect different noodles, you quickly get down to a much smaller space. Okay, that's the game. I will just go through the mathematics, and this is just explain all this whole thing, and it just show you one example. When you take a model, hydrogen CO, subject it to this type of uncertainty minimization analysis using very wide range of experimental data, including laminar flame speed, covering a range of pressure, ignition delay time, covering a range of temperature, flow reactor, laminar flame species profile, and so on and so forth. This is for hydrogen CO oxidation. You'll find that considering no experimental constraints, you get this original 2 sigma band given by this 2 dashed line. This is what I showed you earlier. Once you constrain the model based on knowledge before this set of experimental data were made available about 5 years ago, you get this band, substantially smaller than that. And then if you put this set of data into the model uncertainty minimization, you'll get, of course, a substantially smaller band. The net effect in the rate constant is that you cannot pin out an individual parameter. There's a coupled problem. Okay? But what you can do is, don't worry about this. This is not important. To illustrate this problem is, this is my initial entire uncertainty space projected onto the 2D space of this particular rate parameter. It was a, well, normal distribution. And then once you joint probability density function is plotted in a contour form, once you throw all the experiments on them, then you narrow this uncertainty space, although coupled, down to a much smaller space. Mathematically, you understand what I'm talking about, right? Conceptually. Mathematics of the problem is there are many ways to do this problem. Okay. So this is how we should deal with that problem. So why aren't we doing it as a community? Well, it's because it's hard. I have a project. I need to develop. I promise that I'm going to deliver a model at the end. And I have students who need to be funded to work on this project. At the end of the 3-year period, I have to deliver this model, and the student have to write a thesis to graduate. Now I have to coordinate it with other people to come up with a consensus model. So my student life becomes a lot more difficult. It's a valid approach because you're emphasizing the fact that you have to do them. Of everything that I do, the most important thing is the student. And the science accompany that. So this is, in a way, a sociology problem that we cannot solve. Okay? Can we? Well, we've been talking about this problem in this community for at least 10, 20 years. There have been no solution. So then an unscientific conclusion is going to occur. Whoever can get the money last till the last minute before the science dies gets the truth. The last model win. Okay? It isn't the best model win, it's the last model win. All right? I'll leave this problem question open for you guys to think about it. All right. This is actually number 3, the real field and the large model problem. I want to make sure we have enough time towards the end, so we're doing well in time. The third problem I want to talk about, this is not a 2, this is a 3, is the real field problem. We talked about this on Wednesday quite extensively, and I just want to show you an example of how large model problem can be solved. Before that, it was a many model problem. This is true even for hydrogen. Hydrogen is the foundation. If you change the foundation, everything changes. From there, you can bifurcate, of course, infinite number of models from there. The other problem, and the spectrum of the problem is the large model. The large model that I showed you earlier. You have number of reaction, number of species. These are for hydrogen, methane oxidation. This is for some biofuel and jet fuel up there. We have about 100,000 reactions, 10,000, 100,000 reactions in the model. About 10 to the 4 or 1,000 to 10,000 chemical species. All right, marching along this line, indeed, we started here about 40 years ago. We got to here about 20 years ago. We got to here about 10 years ago. Now this is today. They're just getting larger and larger. Larger and larger also means more and more parameters. When Dixon Lewis started this business, he was working on things down here. About a dozen, 2 dozen reactions, about 7, 8 chemical species. That problem, in terms of number of variables, is like our solar system. You have to agree with me. Mapping out the position and the momentum and the trajectory of each and every one of these planets is a major scientific triumph for us. After all, this system ought to be modeled by knowing exactly where about, what mass going at what velocity for all of these planets. Agree? That's the only way we can make predictions. If you want to land on Mars, you better know this to the last mile. Okay. So that's about a dozen parameters. We can solve this problem. When you go to there, you have 100,000 of reactions. So in analogy, you're looking at the Milky Way galaxy. If you allow me to make this analogy, then you will not think that a model for the Milky Way galaxy by knowing the position, the mass, the velocity of every planet, every star is a good model, right? How would you do that? There has to be a different way to treat this problem. Okay? Something even chemically, physically similar of the same principle down here for this system is not necessarily the same as far as our approach is concerned for a problem of drastically larger size. So something has to be done for this system. This system is the real field problem. We talked about earlier that clearly in any large field combustion, the fuel must crack down to a smaller number of soup. These are typically ethylene, propane, hydrogen, methane, and so on. And it shall do so always, as long as you burn the real fuel with many components in it, but with a known hydrogen to carbon ratio, with a known enthalpy of formation, because this defines more important thermodynamic properties of the system. And the question is, based on this physical observation, how do you construct a model, and how do you best utilize the experimental and theoretical capability available to us to achieve the goal of some prediction? All right. So you take a real fuel, you know it's undergoing pyrolysis. What it produces is ethylene, hydrogen, methane. And I call this as a base set species. All right. Nature has cleansed this fuel for us in a flame front, leading to a small set of fragments. And yet the oxidation of these fragments, leading eventually to the production of carbon dioxide and water, is rate limiting. Okay? We know it's always rate limiting. For that, without that step being rate limiting, we should expect to see a great wider range of combustion phenomena than we are seeing here. All right. This whole process is all about, as I always trying to find a photo to show you, that this is all about school bell ring. Children rush out of school, and they must go through one same door. Do you have this image in movies in you? So the jam is always at the door. Kids running out from different classroom, okay? And running through the walkway. At the end, the whole rate at which kids exit the school is determined by how big that door is. And that door, in combustion sense, is the oxidation of CO to CO2. The last step is rate limiting. That's the slowest. And that step also releases heat and gives you hydrogen atom. And for that reason, this process is controllable. You don't have that many knobs to turn. You make this door a little larger, kids will just go out of the school a little faster. You want to control the flow, you want to slow that down, well, shut half of the door. Alrighty? And they all, of course, students start to congregate in the same walkway, just behind the door trying to walk out. This is the same phenomenon. All right? So to do that, the basis set is produced from endothermic process. We talked about this, driven by entropy. And distribution of this product is thermokinetically constrained. And how large is this basis set? We know now today that there are only 1, 2, 3, 4, 5, 6 species you need to worry about. 6, because of thermodynamics. And then this part is rate limiting, and you better describe it by detailed modeling. In doing that, you can simplify this batch. It's this bunch that's responsible for the larger size here, down to something that's very, very small. And the way how you achieve that, look at that, is to do experiment. So can the distribution of the base set be mapped experimentally? And I'll show you examples. The answer is definitely yes. Okay. So if you were to postulate a model, this is rather busy, but let me just show you the essence of it. Okay. You take a few CMH sub n. You ask this reaction to be broken down into, allowing the fuel to be broken down into ethylene, propane, 1-butene, benzene, toluene. with some radicals. Okay? Once the radical is produced, it attacks the field to form, well, for example, if R is H atom, then RH is H2. And also produce now ethylene, propene, butene, and so on, the same type of product. And you should describe this process pseudo-kinetically. These are often called a global reaction. And a global reaction with the assumption that their stoichiometric coefficients are not function of temperature and pressure. Then we make this assumption, we test this assumption to see if it's valid. Okay? And these are caveats for those parameters. As a matter of fact, your initial carbon to hydrogen ratio gives a very strong constraint on what choices of this stoichiometric coefficients you can take. Why is it? It's because my dominant product is being ethylene. So that if I start from a jet fuel, typically N is equal to 2 times N. Hydrogen to carbon ratio in a jet fuel is 2 to 1. If I produce ethylene, propene, and 1 butene, I'm not perturbing this ratio. Okay? Only when I form aromatics, I must balance this out by producing more methane to balance, keep the hydrogen to carbon ratio the same. One has a smaller hydrogen to carbon ratio. The other must have a higher hydrogen to carbon ratio in order to make the element conserved. All right. This allows us to establish, well, algebraic relation among these parameters. And as a matter of fact, in constructing any chemical reaction model, the number one constraint you have is mass conservation or element conservation. The second is thermodynamics. The third, only the third is kinetics. How fast you get there. So it turns out that you ask the question, well, what are the possible stoichiometric coefficients I can choose for a field having composition C11H22? Then there aren't that many. They're highly correlated. For example, if my ethylene yield per field is, say, around 3, then my methane can only be this much. There's no other option, just because elemental conservation. All right? You cannot arbitrarily choose ethylene and methane yield. You can only do this following this band. And the variation of this band all has to do with some other finer parameters. It's not that important. If you look at this is numerical. This is just a simple algebraic relation. And at the end, we have a problem of alpha, beta, lambda 3, lambda 4, chi, and one more parameter that we need to determine. 6 parameters now. You reduce thousands of chemical reaction or thousands of rate parameters down to 6 parameters plus 6 rate constant. This is, well, if R is equal to H, methyl, total add together, we have 3 rate parameters. And to be more generalized, I expand this list to include O, OH, and H2O. If you will, I have a total of 6 rate parameters and 6 stoichiometric coefficients. A problem of 1,000 parameters is reduced down to 12. Let's see if this model works. This is how we get them. It's all in the details. Let me jump through all this. So let's say I went to Professor Hansen's office and said, Ron, here's a JP8. Could you do a set experiment for me? What I need to know is ethylene time history and methane time history. I have 2 parameters available. I go to Professor Bauman's office and I said, can you measure for me the ratio of propene to ethylene? For that ratio gives me the value of lambda 3. If he can also do the measurement of 1 butene relative to ethylene, I got the lambda 4. Then he can measure toluene to benzene ratio during the pyrolysis process. I get 3 parameters coming from flow reactor, and I have 2 detailed time history from shock tube. I have 5 observations, but I have 12 parameters. The 6 rate parameter, I don't know anything about it. I just assume them to be all equal to the rate respective rate coefficients of n-dot Aiken oxidation. I'm still one observation short. But that's not true because this has a time profile. This measurement is not one-point measurement. It's a time history that it gives us additional information about these radicals. If I produce more hydrogen, if I push up hydrogen production, reduce methyl production, this line would go a little faster just because hydrogen ion is more reactive than methyl. So I actually have more information than I need to back them off the model, the six stoichiometric coefficient. The validity of this model can be shown by this. Remember, I'm going to make an assumption that these parameters, or stoichiometric coefficients, are independent of temperature, independent of fuel concentration, independent of my thermodynamic condition. And obviously, it's an assumption. An assumption is valid, if it's valid, it's going to be valid within a range of conditions. So through this experiment, we found that this assumption is valid up to about 1450 Kelvin. Then things start to fall apart. Okay? This is the yield of ethylene and methane as a function of a temperature at a given reaction time of 0.5 millisecond for an actual JP jet fuel. There are three of them, A1, A2, A3. A1 is jet A, A1 is JP8, A2 is jet A fuel, A3 is JP5. Now you realize that this is pretty good. Okay, I can use one single model, couple reaction steps to describe a fairly wide range of data. Number one. Number two, remember one thing I said the other day? Why shouldn't you worry about stepping into an airplane without having to ask, where did you guys get that tank of jet fuel? Jet fuels have different compositions depending on where you buy it. You go to Russia, Russia has its own jet fuel. Airlines don't carry their own jet fuels. Different countries produce different jet fuels. This may come from different oil fields. The reason you shouldn't worry about it is because it doesn't matter what jet fuel you burn. In the flame front, composition can be very different in the original fuel. Once you pre-process this fuel in the flame front, they all break down to exactly the same thing. Look at that, the three fuels. Ethylene, identical. Methane, identical. This is as if you ask the question, well, what is average height of people in New York versus average height of people in California? You won't find them to be very different. Okay? Multi-composition complex fuel have one advantage. The rule of a large number. When you have enough components, you average them out, you always get the same answer. This is not true if you take an arbitrary person from New York, an arbitrary person from California, and asking, are they of the same height? Most likely the answer is no. So multi-component mixture, in that sense, gives us a simpler, easier solution than single component fuel because of statistics, because of the rule of a large number. And in the statistical realm, this is called the central limit theorem. Okay? Physical science panic when I don't know the composition. But statistics always come to save us. And you will not answer the question, what would be the average height of people in New York or people in California by going to measure everyone's height, right? That's a terrible thing to do. Okay? And that is a fundamental difference between, for some of you who have worked on surrogate mechanism, a surrogate approach, versus this approach. This is the fundamental difference. Okay. How well is this approach? This is how I got the rate parameter. I already talked about them. And now I have a problem that is constrained. I have enough experiment to back out the model parameter. How well does this model work? Now this is not fudging. I have not tuned any parameter. I just determined those parameters from this type of experiment and take it all the way to predicting, asking, does it predict my ignition delay time of jet fuel? It does. The model was developed only for the pressure of a 13 bar and giving initial delay for the stoichiometric mixture between experiment symbols and the line is a prediction. And it doesn't do as well for the rich mixture at equivalence ratio of 2.1. I don't know why yet. This is only a few months old. Okay? There may be something missing in the model. And this is for the lean mixture of a 0.5. It's not bad. More importantly, the model can be extrapolated to higher pressure, about 50 bar. Comparison between the data and the simulation. This is the laminar flame speed between data and the model. So this approach definitely is viable. So the story and the lesson I learned from many years spent on surrogate approach and about 1 year spent on this particular approach is one thing. When you develop your physical model, you have to make sure, or rather I have to make sure, that the parts of the model, or each and every part of the model, can be independently interrogated by experiment. Without that element, your model will always be highly uncertain. Theory or model without experimental validation is a dangerous business. Okay? And you always want to ask what are the experimental and the theoretical capabilities that are available to us, then write the model accordingly. All right. So what more do I have? All right. That's good. I'm doing well with time. It's only 4 o'clock. We have more time to have fun and discuss new ideas. And this is actually the first slide of the last part of the lecture I want to have. And I'll just describe this and come back and ask. Well, we'll start with this next round of discussion. All right. Before I do that, let me just, have you ever seen this thing before? What NRC, the National Research Council, I believe, listed the top 20 achievements of the 20th century, basically last century. Everything marked red have something directly to do with combustion. Okay? Everything in blue, as a matter of fact, I can illustrate. Almost all of them have to do with something about combustion, indirectly. Directly, electrification. It's combustion. Or combustion is a part of it. Automobile, of course. Airplanes. The top 3 greatest achievements of the last century has to do with our ability to control combustion and convert chemical energy to power. Okay. Water supply, you have to run a pump. A pump needs electricity. Therefore, it needs combustion. Electronics, of course, radio also need electricity to run. Agriculture mechanization, big tractor, trucks. All right. Computers, telephone, air conditioning, all this need electricity, highways for cars to run. All right. Spacecraft, of course, combustion. Internet imaging, all these things had to do with something has to do with electricity, availability of electricity. So the last century, the king of technology advancement was in fact largely our ability to do combustion. For without it, life quality today would still be a lot worse, and that goes without saying. What I don't want to show you is what the NRC states is what they think the challenges for the current century. Mysteriously, many things directly associated with combustion. As a matter of fact, everything associated directly with combustion disappeared. Now, I wanted this to be a starting point as an inspiration for all of us to come up with something interesting, something new, something that will directly impact the society. And we'll take a break. We'll take a 15-minute break and spend some time, think about it, and we will have a collective discussion. We'll start with the discussion about oxy-combustion, and we end up with something collectively. Not necessarily come up with an idea or a conclusion, but in helping us to think about out of the box. Okay?